Hi, I'm Ilya, and today I'm gonna talk about this mobile robot. It's called LeKiwi, and it was developed by SIG Robotics and the University of Illinois at Urbana-Champaign in collaboration with LeRobot. I will talk about how to start with this robot, how to assemble it, how to control the robot remotely, collect dataset, and train autonomous policies. So let's get started. This is the main character of this video. It's called LeKiwi, and my version is not the default one. So actually, it's pretty heavily modified. I use some custom cameras. I use custom gripper. My front camera is rotating together with the robot. I also added this top extra layer that allows you to add one more top view camera, and it can be attached on top of the robot like this, and you will see it in this video many times. So sometimes I will use the more default version with just two cameras and no top layer, and sometimes this upgraded version with extra top view camera. But regardless of all these modifications, it's still the same robot, and everything that I will be talking about is applicable to any version or any modification of LeKiwi. This robot consists of two main parts. It's conveniently that they have different color in my case. So the top part is just SO R100 or 101, and simply speaking, it's this robot. I have a big video about it describing all the steps that can be useful to start experimenting with this robot, so you can just follow the link and check it out. I would definitely recommend you to watch this video because everything that's applicable for this robot is also applicable for the LeKiwi, and I will try not to repeat myself too much in this video. So, like, if you haven't seen it, I strictly recommend to do it right now. And the mobile base is basically what distinguishes this robot from the arm itself. So it allows it to move in any direction or rotate in any direction. And you can do much more different tasks using this robot because your arm is not longer static, it can move in the space. This base has three Omni-Wheels, has three motors that are the same as servo motors in the arm itself, so it's very easy to control them. And also it has, in my case, Raspberry Pi that actually controls everything, and a battery here. This base will cost you extra, maybe $300 on top of the cost of the arm. I think was wheels and motors a bit pricey, but I think there are already some options how to get like cheaper wheels or even 3D print them. So you can search in the community and maybe find some alternative options. Overall, I would say there are much more variability of components of this robot than in the original arm. So you can be much more creative and try to do a little bit different things. Before we move to the robot actual capabilities, let's quickly talk about 3D printing and the assembly of this robot.
The mobile base is mostly 3D printed and uses the same motors as the arm. It took me a couple of days to print all the parts, but the actual time will depend on your printer and how you distribute the printing. Some parts you will likely need to adjust for your setup. If you're using non-standard cameras or batteries, you will need to print custom mounts for them. There are several components variations available. You can use different wheels, different batteries, or different single-board computers to control the robot. Just follow the BOM listed on the repository and find the best parts available in your region. I will also share a repo with my custom parts in the description. After everything is printed, the next step is assembly. Just follow the instructions in the original repo, and it took me a couple of hours to assemble the robot. Pay attention to the small parts required. Unlike SO arm, the LeKiwi needs extra screws and nuts that aren't included with the motor. I initially missed this and had to improvise to fix it. Even if you plan to run it using a battery and a single board computer eventually, first I would recommend you to test it using a cable. Just connect it to the power supply and your computer. It's easier to debug if something isn't working at this stage.
manual control of the robot is called Teleoperation. And the most default way to do it is by using the keyboard of your computer and the leader arm. You can use a keyboard to move the mobile base like in any direction and also rotate it. And you're using the leader arm, like the one right here, to control the actual arm of the robot, the follower arm. So you can see whenever I'm moving my leader arm, the follower arm is making the same movement. So you can control gripper, you can control any joint of the robot by simply moving the leader. It's actually completely the same as controlling the simple SO arm. So again, you can just refer to my old video where I discuss more teleoperation options. Also, there are not so many default ways to control the robot, but especially after the recent update, LeRobot allows you to integrate new teleoperation device into the library pretty easily, and there are a lot of community effort in this direction, and different people actually integrate different teleoperation controllers into the library. One very common thing is to integrate different gamepads and controllers. But another example that you can see right now in the video is what I developed during the LeRobot hackathon that happened a few weeks ago. And this is a simple Android application that allows you to control the robot remotely, and also all the video from the cameras is sent directly to this application, so you can see it on the screen. You have joysticks that similar to like joystick in video games, and you control both arm and mobile base using this device. To be honest, I would say that using the leader arm is still the most convenient way to control the arm itself, but I think for the mobile base, there are better options than simply using the keyboard. By the way, if you want to try, all the code for this application is open source, and I will also provide the link in the description.
LeRobot uses rerun that allows you to see the stream from cameras during the teleoperation. So in this mode, I can see what's happening with my robot, can control it, and can also move the arm itself, and immediately see what's happening and what's changing in the cameras. You can also see all the actions and all the states here on the chart. And yeah, it's very convenient to control a robot like this. And I would say it's a very good exercise and good practice in the beginning when you just assembled your setup to try to control your robot using only these cameras. It's not strictly necessary for data collection, but it's a very good heuristic, because if you cannot control robot using cameras yourself, how do you expect the policy to control the robot? You can see my top camera is slightly shaky whenever I move it. It's shaking, but yeah, I will fix it later. When you control your robot using cameras only, you will also be forced to do some exploration. For example, you see, like if I move camera like this, then wrist camera becomes pretty useless. But if I move camera like this, it's a nice front-looking view. So if I would control my robot without looking at this video, at this images from camera, I would probably not care about the position of the wrist. But when I control it using camera, I kind of forced to do some exploration and find the best position for the camera to have the best view on the environment. And the policy, when you train it, will learn how to do it autonomously. Your policy will know what to do with the cameras to get better view on the environment. Yeah, so this is how it works. Quite enjoyable process to control robot like this. So let's see what the mobile base is capable of. So first of all, of course, it can move forward as any remote control car, and it can move back, and also it can rotate in place, again, as many robots or RC cars. But what is really nice is that this robot also can move sideways. So it can move to the right, it can move to the left.
And you can combine any direction and any rotation at any moment. So, for example, if you simultaneously move forward and to the right, you'll just move along the diagonal, and you can move the same way in other directions. And you can also combine rotation and side movement. So, for example, here I move to the side and I rotate the same time. And in this case, the robot rotates around some point in front of it. If you rotate to the other side, it will start basically rotating around some point behind the robot. So you can see these are very strange but nice and fun moments. And this makes this robot is very capable of moving in some hard environments, and it's very easy to control, and it gives it very high maneuverability. I already mentioned that this robot uses this special type of wheels called Omni-Wheels. So let's have a closer look and discuss how these wheels work. Okay, so first of all, Omni-Wheel is a wheel. So if you take this wheel, if you connect the motor, start rotating this motor, this wheel will move forward as any other wheel, and there is nothing specific about it. What is specific is that this wheel also has a lot of these rollers everywhere that are very easy to roll without much of the friction, much of the resistance. So the idea is like if you push this wheel from the side, it will freely go sideways without even need to actually rotate the motor that is connected to this wheel. So it means that at any point in time, this wheel can have velocity that consists of two components. Component number one is along the wheel dimension, and it's basically generated by the rotation of the motor attached to this wheel. So when motor rotates, the wheel is moving. Component number two is not generated by this motor, and it has a direction that is orthogonal to the main direction of the wheel. And if you have one component directed this way, one component directed this way, then eventually your wheel will start to move diagonally. And it can move in absolutely any direction like this, so you just need to combine the rotation of the wheel with this sliding thanks to the rollers, and you will get like omnidirectional movement of this wheel. This is why they are called Omni-Wheels, and they allow to move robot in any possible direction, in any combination of velocities, both linear and angular, when you just have these three wheels and control them by rotation speed of three motors. So let's dive deeper into the kinematics of the robot that has these three wheels attached as in LeKiwi.
Let's try to derive formulas for the forward and inverse kinematics for this robot. Let's say that our x-axis is like looking forward in response to forward movement, and y-axis is orthogonal to it, and positive numbers corresponds to movements to the left. So in our case, then the positive direction for rotation will be counterclockwise. And also we can describe the position of the wheel by just providing the angle between the mounting, like this line connecting the center of the robot and the mounting point of the wheel and the x-axis. It's important to mention that if you want all formulas to work for all wheels and be universal, we need to pay attention to the kind of direction of the angles. Okay, and finally, let's denote the velocity of the center of the wheel as v, and represented by this purple vector. And this velocity, as we discussed, have two components. So the one component is the actual speed of the wheel rotation that will exist for any type of wheel. And the second one is orthogonal to it, a velocity that comes from the rollers. And this velocity, this part of velocity, we get for free. And yeah, these two vectors, the orange one and the green one, they are orthogonal. And if we sum them up, we will get the total velocity of the center of the wheel that is mounted to the robot. And yeah, finally, we can see that the angle between this roller related velocity and x is the same, is alpha. And then the angle between this green velocity of the like main velocity of the wheel and the x is just shifted by 90 degrees because there is like 90 degrees between these two vectors. So it will be alpha minus 90. And also you can look at this triangle, and you can see that if we know this total velocity and we know the angle between the green and the purple lines, then we always can compute the velocity with which the center of the wheel should move in the this main direction by just multiplying v by cosine between v and vw. And we will use this formula for all the derivation in the next pictures. Now let's consider a few simple examples. Example number one, when we want to move robot strictly like forward without any side movement and without any rotation. So here by this red line, I just show the direction of robot movement. So this vector is not really equal the actual speed, but it just shows the direction. But if our robot, the whole robot is moving forward with some velocity, then every kind of point of this robot, including the center of the wheel, will move with the same velocity forward. So it means that center of the wheel should also move strictly forward, and it means that our like Vx equals V. And then we can just put this Vx into this formula to get the this velocity of the wheel, the green one that we want to find. So we just put it there and then just put all the angles that we know, and we can get that velocity that comes from the rotation of this particular wheel should be simply equal Vx multiplied by sine alpha. Then let's say we want to move to the right or to the left, and we have some vector Vy that representing this movement of the robot. And again, the logic is the same. So all the points of the robot will move with the same velocity. In this case, the this green velocity of the wheel should be simply equal Vy multiplied by cosine alpha. So now we know the solutions for these two simple cases. And the third simple case is when robot is not moving forward, backwards, or sideways, but it's rotating. So it means that all the points are just moving around the center of the robot without robot actually shifting in the space with some angular velocity omega. It means that the velocity of every point of this object should be orthogonal to the line connecting the center of rotation with this point. So basically it should be like tangential to this robot circle. And in our case, it simply means that there is absolutely no component that is related to the like rolling of the wheels sideways, and the whole rotational velocity is the same as the velocity of the rotation of the wheel itself. So in this case, the formula is very simple. So our green VW is simply omega multiplied by r, where r is the radius of the robot. But now let's look at the more general example when we have some movements in all the directions, and so we move forward or backwards, and at the same time the robot is moving sideways, and at the same time is rotating. And the nice thing about it that we can simply sum up all the vectors to find the final vector that is describing the direction and the speed of the center of the wheel. So we take the component that corresponds to the movements like forward along x-axis. Then we add the component that corresponds to the movement along the y-axis. And finally, we add the component corresponding to the rotation. And if we sum all of them up, we'll get the final vector representing the velocity of the center of the wheel if our robot is moving in all direction and rotating. So the nice thing that we can also simply sum up all the components, and if you want to get the final value for our like total VW, then we should simply sum up all the things that we derived in the 3 previous simple steps. So if our like, movement is complex and consists of both like x, y movements and rotation, then the final formula for the required velocity of the center of this wheel will be just sum of all these 3 formulas that we derived. But we usually don't care about the linear velocity of the center of wheel. What we care about is the rotation speed of the wheel, because this is what we can control by sending some commands to the motor. But it's very easy to convert this velocity into the angular velocity of the wheel rotation. We just need to divide everything by the radius of the wheel. So if we do it, and if r is this radius, then this will be the final formula. And again, as I said in the beginning, the difference between these 3 wheels is only the angle at which they're connected to the robot. So formulas for other 2 wheels will be exactly the same. We just need to replace this alpha with different corresponding alphas. And if you write it down in the matrix form, we will get this simple matrix that converts the velocities of the robot into the angular velocities of the wheels. I used numbers 7, 8, and 9 in this case because first 6 numbers from 1 to 6 I used to refer to the motors in the arm itself. And this like 7, 8, and 9 are officially used as numbers of the motors corresponding to the wheels of the robot. So I use these numbers. Okay, so this is called inverse kinematics, and this is what we just derived. So our inverse kinematics again in the matrix form looks like this, and we can, for simplicity, call this like 3 by 3 matrix A. And if you want to derive forward kinematics, we don't need to like use any geometry. The only thing that we need to do is just to solve this system of linear equations, and we will do it by simply inversing the matrix A. So if you inverse matrix A, then we will get kind of formulas that can transform all the angular velocities of all our motors into the actual velocities of the robot. And you can solve it analytically. So if you solve it analytically, this will be the solution. But for example, if you look at the code of LeRobot, then they don't, I think, even solve it analytically. They just use NumPy to invert this matrix, and it works just fine. So it's kind of pretty fast. So you don't even need to solve it, but I solved it anyway. And I think it's kind of more straightforward and use less computations if you already solve it. And another thing, because I already mentioned the code of LeRobot, I think in the LeRobot, in the library, they use slightly different notation, maybe slightly different coordinate directions. So the actual formulas that they use is slightly different from what I use here, but they are actually identical. They just again a little bit different definitions, how they compute angles and how they direct all the x and y axis. So idea is completely the same there, even so formulas can look slightly different. And finally, for our case, where we know actual alpha for all the motors, we can compute the actual numbers, all these sine, cosine things, and this is what we get. And when you look at these things, you can actually find some, I don't know, simple things for sanity checking. First of all, you see some symmetry in the thing. So we have like 2 wheels that are pretty kind of symmetric, the 2 front wheels. So whenever we're talking about movement forwards, they should move in the into opposite directions, kind of, such as both of them are actually moving forward. So this is why one has like negative side, one has positive side, but the absolute values of these two numbers are the same. So this is because of the symmetry. And then if, for example, you look at this 0, then the 0 says, and like the corresponding 0 here, this 0 means that there is no impact of the back wheel number 8, and the speed or like velocity along the x-axis. That also makes total sense because the back wheel completely orthogonal to x-axis, and all the movements of this wheel along this axis are only because of the rollers. So you never need to like rotate this wheel to move forward or backwards, and vice versa. If you strictly move forward or backwards, the back wheel is not rotating, and this is the meaning of this 0. It also makes sense. And another thing that also can come from the symmetry is that this column and this row, they have the same numbers. This is because this column and this row, they are corresponding to the angular velocity of the robot, to the like rotation of the robot, and all the wheels are symmetric respective to the center of the robot. So the actual rotation should always be kind of the same. There is absolutely no reason for them to be different just because our robot is completely symmetric. So yeah, these are just like some sanity checks that you can do when you look at the numbers like this. But overall, I think that this is nice exercise as you want to better understand how all these kinematics of different type of this Omni-Wheels work. It's a nice thing to try to derive it yourself. Also, if you want to make some robot with unusual unusual setup, with unusual location of the wheels or some different wheels and so on, you can always use the similar logic to derive all these equations. Yeah, that's it. This is how this robot moves and how we can connect the angular velocities of wheels rotation and the actual robot movement velocities. Now, when we know how to control the robot, we can start recording the dataset. So, dataset is simply recording of you teleoperating the robot to complete some task. In this example, I want to just show a very simple task where my robot grabbed this boba tea toy, and to teach it to do it autonomously, I recorded around 60 episodes in different parts of my Conda, in a little bit different locations, a little bit different lighting and different backgrounds. And yeah, you can see some of them in this video. For this exercise, I used only 2 cameras, so I don't use top view camera here. You can see it's disconnected. I operated the robot completely remotely, so I was sitting in a different room, so I couldn't see what's happening with the robot from the outside. I was just relying on the video from cameras from the robot itself, and was controlling it using the keyboard and the leader arm. When you collect dataset to train the policy for the arm only, it's usually enough to collect like 30 to 50 episodes for a simple task. In case of mobile robot, we want it to be more robust, we want it to generalize better for new environments, so this is why you need to collect more data in general. So for this simple task, 60 was more or less enough, but I still feel like I needed more to get even better quality. After you collected the data set, you can train the policy and your robot will learn how to do this task autonomously. The policy is simply the machine learning model that controls your robot. It gets the signals from the cameras and predicts what should be the next action. And there are a lot of policies that already implemented in the LeRobot library, and you can use them out of the box. I also developed my own policy around like half a year ago. It's called dot policy, and it's pretty simple and small policy that works pretty well on simple tasks. So I decided to give it a try and try to use this policy for LeKiwi. I had like some concerns before I started to use it, because one of the things that I assume in my policy is that what we predict are actual positions of the motors, but in case of LeKiwi, you also need to predict velocities. And there is slightly different logic in how we aggregate the predictions and so on and so forth. So I wasn't sure that it will work, but eventually it worked, and it's pretty nice policy that works with LeKiwi as well. Here you can see the actual policy rollout. I simply train it with mostly default parameters using these 60 episodes that I collected, and I would say that it trained to complete the task. Maybe not as good as I would want it to do it. This video has the actual speed, so it's not speed up, it's the real speed. And I would say that the success rate is maybe around 50% in the locations where I actually collected the training data set, but it's lower when I move it to the new location. So it maybe goes to like 20 or 30% when I move it to locations with new background that robot didn't see before. So I guess that for the actually generalizing strategy, we need much more data and more diverse data. Also, you can see here that yes, quite often the robot fails. As I said, the success rate even in the known locations is around 50%. But I would say even 50% is pretty good after 60 observations for this robot, given, as I said, that I didn't even expect that it will work well with velocities, and it seems it works pretty well. I'm pretty sure if I collect more data and also try to optimize the policy a little bit, maybe by adjusting some parameters and so on, then I can get much better results for this task. Because both parts of the like logic of the process seem to work. You can see that robot can actually move towards the target pretty well, and when it's in front of the target, it can grab it. So it sometimes some issues happen, but probably it's because of some strange location that is not that wasn't represented in the data set. You can even see that it can adjust its position. It's not just moving forward or backwards. It can move sideways. I didn't see it rotating much, to be honest. It's probably because I didn't have too much rotation in the data set. It's didn't train how to properly rotate towards the target. But yeah, overall, you can see that it works. It works pretty well. It works pretty fast. And definitely dot policy can be used with LeKiwi. Another important thing to discuss is performance, and we want to use LeKiwi as a mobile robot. It means that we can actually run policy on the robot itself, or we can run policy remotely, and then a robot should just send the observations to another computer, another server. We make predictions on this server and then send them back to the robot. I tested 3 different options how to control the robot, how to run the policy on the robot. The first one is using Raspberry Pi that you've seen is installed on my robot. In this case, I run policy on the robot itself without using any other computer, any other server. The second one is when I run the policy on my Mac. So I have MacBook with M1 processor. It's like 3 generations behind the latest processors from Apple, I guess. But it's still pretty good. So yeah, I don't have any GPU on this laptop, just this Apple processor. And finally, also pretty old, also 3 generations behind, I have a computer with GPU. It's 2080 Ti. Maybe 7-8 years ago it was powerful one. Now it's not considered powerful for sure. And what I wanted to test, I wanted to run 3 different policies on these 3 different devices. So I used my dot policy that has the just 14 million parameters. I used ACT policy that use 52 million parameters, and I used diffusion policy that has more than 200 million parameters. For all of these policies, I use the same inputs. I use 2 images, 640 by 360, and all of them predict 30 steps forward. So it means they predict around like 1 second, because my FPS is 30 for both the cameras. The only exception is diffusion. Because of some parameters limitation, it needs to predict 32 steps, but it doesn't make much difference. And for the first test, I used n action steps, or in case of dot policy, it's called predict every n parameter set to 1. It means that I try to make the prediction of the model after each frame that I receive from the cameras. And you can see the predictions per second, or like actions per second, in this table. So you can see that when I run it directly on Raspberry, it's very, very slow. So I make like 1 prediction per second for dot, even less than 1 for ACT, and it's basically 0 for diffusion. It's like takes forever to make prediction on Raspberry for diffusion model. Again, I just use a model with the default parameters. On Mac, it's much faster. So when I run it on Mac, it's already pretty good. So like 20 predictions per second is good enough to really run the policy in real life. So the policy works very well. ACT is pretty close, also reasonable predictions, but yeah, both of them we don't have enough performance to predict it, to make predictions for every frame. And finally, diffusion is still pretty slow. And then when I run it on my computer with GPU, it's almost so close to the case when you connect your robot directly to this computer. So the time that takes to send images and receive actions over Wi-Fi network, pretty negligible in this case, so it works very well. But diffusion policy still stays slow. We make almost 1 prediction per second. That is still not so good. But actually, all of these models, they have different optimization for this case, specifically for this case. And one of the most common optimization is instead of making predictions for every frame, make predictions once in a while, few steps forward, and then make these steps, make these actions, and then predict the next steps. And usually it's controlled by this parameter and action steps. So I ran another experiment when I set it to 10, and you can see that results improved everywhere. So if you look, let's go backwards this time. So on 2080, dot and ACT basically work in real time. Diffusion is still pretty slow, and it's like very shaky. It's not nice how robot is moving in this case, but probably with more powerful GPU, or maybe with some optimization of parameters, you can make it work, because it's already at least started to be in the reasonable range. Then on my Mac, also dot and ACT running very fast, so it's actually very usable. Diffusion probably not so usable. So if you want to run diffusion models, I would recommend you to have some GPU. And on Raspberry, it's again, it's better than 1 prediction per second, but it's still pretty slow. And also you can see that dot policy get smaller boost than ACT policy. In dot policy, I use multiple past observations, And this is why I still need to make predictions for some past images from the cameras, and the improvement in speed and performance is not as big as in ACT. So when you run it on Raspberry Pi, they actually are very, very similar. Yeah, so the first conclusion is that if you run it directly on Raspberry Pi, it's actually pretty slow. So maybe it's not the best option. So there are other single board computers out there. For example, Jetson series from NVIDIA should be much faster for this type of problems than Raspberry, but I don't have any like last generation Jetson at home, so I didn't try to test it. Even so, I've seen there is like official version of LeKiwi using it, so I think it can be a good alternative if you want to run it locally. But the good news is that even over Wi-Fi, even over my home network, there is no extra delay, and I can run policy either on my MacBook or on my computer with GPU, and they work pretty fast. So it's actually cool. It means that we, in these cases, at least in my case of experiments at home, I don't really need a powerful hardware on the robot itself. Up to this point, we're talking about the basic things. So how this robot works, how to assemble it, how to teleoperate it, how to collect data set and train your policy. You can learn about all the things from the official robot guide. So I think they're very nice. I would definitely recommend you to just go through them and read them and do all these things one by one. But I think the most interesting part of robotics starts when you kind of finish the official guide and you start experimenting. So when you start to change your robot, when you start to try to like invent some new hardware, new teleoperation devices, or maybe write some new code or try some things that are not available by default. And I think it's like very interesting part, and I would definitely encourage you to try to do some extra experiments and try to go just beyond what's described in the instructions or beyond what you see other people are doing. And I think this is when you actually learn, and also this is where the most of the fun is. And in the end of the video, I just want quickly show a few of my experiments of what I changed, what I tried, and so on, because maybe it will be inspirational for you, and you will come up with like new ideas of what you can try. First of all, I already mentioned it, but just want to discuss it like in a little bit more details. I use pretty modified version of LeKiwi. So some of these modifications I already covered in the previous video. So for example, I use this gripper that is different from original saw arm gripper. It's symmetric, it's kind of transparent from the side, I'd say, and for some tasks it's much more convenient than the original gripper, but also this one has some problems, so I think eventually I will replace it too. And will either develop a new gripper or we'll just find something that developed by community or just sold somewhere. Another thing, I experimented a lot with camera mounts. So again, in my old video, you can see some other ways to mount this camera. I printed numerous versions of this camera mount. I tried to put it higher, lower. I experimented with different angle. I experimented a lot with camera lenses. So like sometimes for some tasks, it's more convenient to use wide lens. For some tasks, it's more convenient to use narrow lens cameras. So yeah, I did a lot of tests, just try to like teleoperate and try to train the policy, or did some other experiments with different cameras. I replaced the mount for this forward-looking camera in the original version of the robot. If I remember correctly, this camera is mounted directly to the like bottom platform, and it's not rotating when the arm is rotating. And I think this setup is much more convenient and gives you much more information for the when you grab some stuff, especially when you grab it from the floor. So this camera that always looks in the direction of the robot arm is more convenient than the fixed one, at least in my experience. The only problem with this right now is that
I cannot rotate it too much to the left or the right, but again, it's not a problem for mobile robot because this robot can just rotate completely if it's needed. Then I also did like some small things. So I actually printed a little bit different brackets for wheels, but these are like small. I don't want to talk about it. I printed different bracket for the battery because I just use another battery. So all of these are small. And yeah, the big one, the big addition that you may see and also discussed is this next level. So when I was experimenting with the robot, with the arm itself, I found out that the top view camera is very useful, and really like policies work very well when you have this top view. And usually I used kind of another stand with top view camera in front of the robot, but for mobile robot it's important to attach it to the robot itself, because then you are not limited by like your current position. So then it means your robot can go anywhere and it will always have the camera at the same place. So I developed this like next level and put camera here. Again, as I said before, it's like a little bit shaky because I printed this level very, very thin, so it's not strong enough. I will just reprint it later and it will be much better, much more stable. So I think I will definitely improve it. So it will be more like strong and less shaky. Again, my robot is in the state of constant prototype. I always change some stuff every week. If you look at this robot, it looks like a little bit different. So at some point, yeah, I will make everything a bit more reliable. And yeah, another thing that it helps a little bit with like wire management, because currently I have this camera with pretty short USB cable. So if I wanna extend the arm very far, then it's fine when cable goes here, but it's not enough when cable go directly to the Raspberry Pi. So having it here, having some USB hub here is very convenient. And yeah, so like I think these are all changes that I made for the robot, at least at this point. I also experimented with some different things, but yeah, this is what I did. And I think doing these changes, like making them applying to your own robot, help you understand much better why some of the design choices were made by the original creator of the robots, or you can find some better design choices, or you can even I don't know, come up with some extra improvements that maybe other people didn't think about, and you can even contribute back to the community, contribute back to the design of this robot. So I really encourage you to try to do like some things, to try to do like maybe simple things, or maybe a bit more complicated to modify a robot. By the way, I share all the files for like 3D printing that I use in one of the GitHub repos, and I will leave the link in the description below. LeKiwi uses Omni-Wheels, as we discussed. But there is another type of the wheels that allow you to move in any direction, and they called the Mecanum wheel. And they have very similar idea, but the main difference of these wheels is that the rollers are not orthogonal to the wheel, but they have like 45 degrees angle between the roller and the main direction of the wheel. And generally, in most of the cases, you use these wheels in a 4-wheel setup. So you have like 4 wheels, actually 2 pairs of wheels, because 2 of them have rollers like this. 2 have rollers that are like 90% rotated compared to this one. And then it has like very nice stable kinematics of the robot. But there was like a question, there was some discussion in Discord of LeRobot whether it's possible to make 3 wheels LeKiwi with these wheels. And I had these wheels at home, so I decided to give it a try. And you can see like a short clip right now of how it works in practice. So I would say it's kind of possible, but the results are not so nice, because when you derive all the formulas, you ignore all the like slippery, all the friction and so on. And when eventually you make the non-symmetrical setup, all of these problems becoming very significant. So you can see that it's not very nicely moving in all the directions. But I would say it's kind of nice exercise. So if you want to understand better how kinematics of Omni-Wheels or Mecanum wheels works, try to create some very unusual non-standard setup of your robot. Try to write down all the formulas and derive what are the actual kinematics formulas, and then try to implement it and see how it works in practice. So I think, yeah, even so, I wouldn't recommend anybody to really use this type of wheels. They're not supposed to be used in the 3-wheel setup, but as a fun exercise and some learning exercise, it's actually pretty cool. And if you already have this Mecanum wheel at home, just give it a try. I think it's fun. The last experiment that I want to talk about shows that in the age of LLMs, you don't even necessarily need to train your own policy and collect your data set to make your robot work autonomously. I already talked about this project. I have a long video about it. But briefly speaking, so I developed MCP server and AI agent that can control the robot by using some LLMs. I found out that, like in my experiments, Claude works the best. So I want to demonstrate how it works with this robot. And yeah, when I made my previous video, it worked only with SORM, but I updated it, so now it supports LeKiwi. Now it can even directly run on the, let's say, Raspberry Pi LeKiwi itself, because it doesn't require any computation, and you can create the really autonomous robot controlled by LLMs. So currently it still controls only ARM. I didn't upgrade it to control the actual mobile base. But I will update it soon, so I think it's not so hard to make it also move the robot and let it roam around. So yeah, let's see how it works. Let's look at some demonstration. Let's run the command line interface of the agent and see how it works. So this interface allows me to simply chat with the robot and, let's say, ask it to grab a toy. And you can see that it's communicating using Claude at this case. And it can request or can run some simple MCP tools, for example, to request some extra instructions or to request the position of the robot and the information from cameras. And then by analyzing this information, analyzing the pictures from cameras, it can decide what to do and then send the actual commands to robot. I didn't train it on any tasks. It's completely zero shot. It's just pure LLM controlling the robot based on the just one simple request that I wrote in the chat that you've seen. So yeah, let's see if it will be able to grab it. This time it looks like pretty close. You also see all the thinking process right there in the chat. So it's thinking where provide you detailed information of what's happening, what should be the next steps, and so on and so forth. And let's see, it's almost here. Just need to grab it. Okay, and let's say lift it up 20 centimeters. Okay, and drop it. So yeah, you see that you can control your robot using the simple interface and command line that communicates with different LLMs, and it's cool. So I think it's kind of on the other side of spectrum of possible ways how to control your robot. And yeah, I will also keep experimenting and will try to do something in between, like simple policies and LLMs that are completely controlling the robot. But yeah, like if you want more details, again, just watch another video where I explain how I did it, where I explain exactly how it works, do some like code overview, and give much more details about it.
This is it for this video. I hope you enjoyed it and learned something new. Thank you for watching. If you have any questions or any thoughts, don't hesitate to share it in the comments. As for me, I will keep experimenting and share my experience and results here in this channel, so like and subscribe if you want to see more. And yeah, that's it. So see you in the next video. Bye.